In this video, we will go through the secondary manufacturing processes that follows the primary production and cutting. We will see how these processes affect the properties and applications of glass. As we saw on the previous video, annealed glass is the product of the primary flowed glass process. Annealed glass can be strengthened to overcome some of its limitations. This is done either thermally, by heat, or chemically treating the glass. But the former is most commonly used in the construction industry. In the process, sometimes called thermal toughening or tempering, annealed glass is heated to 625 degrees C, and then the surfaces are cooled rapidly by air jets. As a result, the outer surfaces are cooled down while the inside is still hot. When the glass inside eventually cools down, it tries to shrink and pulls the already cold outer surfaces. This results in a residual stress distribution through the thickness of the glass, where the outer glass surface is in compression and the inner core is in tension. The compressive stress reduces the weakening effect of surface flows, thus increasing its performance, leading to an overall higher tensile strength. The toughening of glass is similar to the pre-stressing of concrete. There are two grades of thermal treatment, known as tempering. Fully toughened, known as tempered, and heat-strengthened glass. Fully toughened glass has the highest level of residual stress and therefore the highest tensile strength of around 90 megapascal, which is 3 to 4 times higher than that of annealed glass. Heat-strengthened glass has a lower level of residual stresses compared to fully tempered, due to a lower cooling rate during the heat treatment process. Its tensile strength is around 45 megapascal, or 2 times stronger than annealed glass. The thermal treatment can also affect the breaking pattern. So, in a fully toughened glass, breaks in small fragments, which reduces injury, whereas heat-strengthened and annealed glass break into larger and sharper shards that can lead to more severe human injury. As an addition, if we want to prevent the glass shards from falling down, we can laminate the glass by bonding 2 or more sheets or plies of glass by means of an interlayer to create strong, safe, and redundant structures after the failure of glass. The most common interlayers in the built environment are PVB and Sentriglass. The interlayer comes in rolls with various thicknesses between 0.38 mm and 2.53 mm, with PVB being the more flexible and Sentriglass being the stiffer. The lamination process starts with washing the glass sheets or plies, which are then stacked in alternating interlayer and glass plies. The stacking phase takes place in a clean room to avoid any contamination. Heat and pressure is used up to 12 bars and around 140 degrees C for PVB in order to bond the sheets together. This can be performed in an autoclave or a vacuum bag setup. The advantages of an interlayer is that it holds the glass fragments in place after breakage, which is important for avoiding human injury. But it also provides residual stiffening even after the glass has fractured. This is known as post-fracture resistance, which is an essential feature of some glass applications like balustrades, floor panels, and overhead glazing. Another advantage of laminated glass is thicker glass components than what can be produced directly from flowed glass, thereby enabling the accommodation of higher loads in bespoke structural applications. Thank you for watching this open glassroom video about flowed glass secondary manufacturing and mechanical properties, where we saw the secondary manufacturing processes make significant improvements to the strength and safety of glass. If you would like to learn more, have a look at our references and further materials at the Open Glassroom platform.